So far, we've dealt with forces that are completely horizontal or vertical. So what do you do when a force is at an angle, neither completely in the x direction nor completely in the y direction? Well, what you're going to do is have a vector that you resolve into the x and y components. Let's say we have a general force F, and we draw our x and y axes, and we know the angle theta that this force has relative to the horizontal. We can look at the components of this force. We can draw a y component and a horizontal component, fx. Now, in order to figure out the components, we note that these fx and fy components are at right angles to one another. Now we have a right triangle, and we can use right triangle trig in order to figure out the components. We know that cosine of theta is adjacent over hypotenuse. The adjacent side is the x component, and the hypotenuse is the magnitude f. So to solve for the x component, we just multiply the f across, and we get fx equals f cosine theta. Similarly, for the y component, we know sine theta is opposite over hypotenuse. That's fy over f. So to solve for fy, we just have f times sine theta. So let's do a specific example. Let's say we have a force with a magnitude of 10 newtons and it's at an angle of 60 degrees with respect to the horizontal. We can calculate fx is equal to 10 newtons times cosine of 60 degrees. Maybe you know your right triangle, maybe not. Let's get out our handy dandy calculator, type in 10 cosine of 60, make sure you're in degree mode, and of course that's equal to 5 newtons. We'll do 2 sig figs here, 5.0. For Fy, we'll have 10 newtons times sine of 60 degrees. Just change that to sine, and we get 8.7 to 2 sig figs, 8.7 newtons. So let's do a specific example. Let's say Gemma the groundskeeper is pushing an old-fashioned lawnmower. That's the kind where it just has the cylinder-shaped blades that run forwards and backwards across each other as the wheels turn. She's pushing that across a flat horizontal lawn. In order to push it, she's pushing down on the lawnmower and sideways at the same time, so that the force is going at an angle of 25 degrees below the horizontal. She's pushing with 125 newtons. The mass of the lawnmower is 15.0 kilograms, and there's friction between the lawnmower and the ground. Now, really it ought to be rolling friction, but we didn't really treat rolling friction. It works with the same type of equation as kinetic friction. We're just going to call it kinetic friction, and we'll have the coefficient is 0.350. And our goal is to find the acceleration of the lawnmower. We're going to solve this problem like we do any force problems with a particular strategy. First, we're going to draw a picture with a coordinate system. Then we'll draw a free body diagram and write a type agent object table. We'll write down all our known values. And then the new part is we'll use the right triangle trig to find the x and y components of the forces with sine and cosine. We'll write equations for all the forces from either the free body diagram or Newton's second law. We'll solve the equations algebraically. Then we'll plug in known values with units and get the final value with units. So let's start by drawing our picture. Here's our flat ground. Here is the body of the lawnmower, the old-fashioned lawnmower with just the cylinder of blades. There's the handle. The blades go back and forth, round and around, and slice through the grass. Here is Gemma pushing down on the handle and sideways. And since the lawnmower is going just to the right, not up and down, it would make sense to use our standard coordinate system. So x is pointing to the right. So now we need to figure out the forces on the lawnmower. I like to start with weight, and so we need to pick a certain number of tick boxes for weight. It doesn't really matter how many tick marks. I like to start with just 3, just to choose a number. The agent of weight is always Earth. And of course, the object is the lawnmower. I'll just write mower since it's a little shorter. What's the next force? Well, Gemma is pushing on the lawnmower, and she's pushing mostly to the right and a little bit down. So we'll draw an applied force in that direction. Now, it doesn't matter if we get exactly 25 degrees. What's more important is that we line it up with the grid marks. So we'll say, let's say 3 over and 1 down. We'll call that an applied force F. The agent is Gemma. And the object is still the mower. Now, I like to save normal force for last, so we have to think about the friction force. Now, it's reasonable to think that Gemma is accelerating the lawnmower to the right, so friction could very plausibly be less to the left than the applied forces to the right. So let's think maybe drawing it 2 tick marks to the left. We said that would be kinetic friction. The agent is the ground. And the object is the mower. Finally, we have the normal force. Now, there's no acceleration in the vertical direction, right? And the normal force eats up whatever force it needs to in order to provide the acceleration in the direction that it's pushing. Well, normal force means perpendicular, so it has to be perpendicular to the ground, which means up. There's 3 tick marks down for weight, 1 for F, so the normal force needs to point upwards with 4 tick marks. The agent is still the ground, and the object is the mower. So now we will write out equations from our free body diagram, or Newton's second law, in order to solve this. So our first equation is the normal force. It's equal to weight plus the y component of the applied force, because those have to cancel out in order for the acceleration in the y component to be 0. Right? But if you're not sure about that, you can always start with Newton's second law in the y direction. And what you would write down is every force that's in the positive direction will get a plus sign. Every force that's pointing in the negative y direction would get a minus sign. So normal force is the only one pointing upward. Weight is pointing downward, so it gets a minus sign. And then Fy is pointing downward, so it would also get a minus sign. The N and the W and the Fy are themselves magnitudes, so those will have positive values, and you're putting the plus and the minus signs out in front of them in order to determine the direction. So all the forces go on the left-hand side, and then that is equal to MAY. But what is AY? It's equal to 0 because the mower is not moving up or down. So the normal force is equal to weight plus Fy. Same as we got from just looking at the free body diagram. Now we're going to write Newton's second law in the x direction. Now these forces don't cancel out, so we really do need to write Newton's second law. Everything pointing to the right will get a plus sign, everything pointing to the left will get a minus sign. So Fx minus Fk, little fk because it's friction, is equal to max. Now, we know from our equation sheet that Fk is equal to mu k times n, the coefficient of friction times the normal force. So we can substitute that in. We're working our way towards solving for Ax, but there's several things we can plug in here. We can either substitute in for n here, or we can go ahead and plug in our trig equations for Fy and Fx. Remember that Fx is going to be equal to F times cosine theta, and Fy is equal to F sine theta. Even though F is pointing downward, we're not going to put a negative in front of F sine theta in our solution for Fy, because over in our equation we already have that minus sign. We're not going to put in an extra minus sign. Theta is going to be equal to our 25 degrees, but we're not going to plug it in yet because we want to solve everything algebraically. So we can write n is equal to w plus f sine theta, and f cosine minus mu k times n is equal to max. Now we can substitute for n and get f cosine theta minus mu k times the quantity w plus sine theta that is all equal to m times ax. Now if you remember from our equation sheet, we have an equation for w, right? And that equation is w is equal to m times g. So we'll plug that in for w. We see that f cosine theta minus mu k mg plus f sine theta is equal to ax. So we're just going to divide all that by m, and that'll be our solution for ax. We know everything on the right-hand side, so now we can just plug in the values. There's a lot to plug in, but we know all of it. So we have 125 newtons times cosine of 25 degrees minus 0.350 times 5.0 kilograms times there's a typo there, 15.0 kilograms times 9.8 meters per second squared, all over 15.0. Plug that into the handy dandy calculator. 125 times cosine 25 Oh, looks like I do have an error in my solution, but through the magic of editing, here is the correct solution. So what changes? Well, we're pushing with less total force, so our applied force vector is going to be somewhat shorter, and the x component this time is going to need to cancel out with the friction component. So instead of going over by 3 tick marks, it would only go over by 2. Now in reality, it would stay at 25 degrees, but just to draw it in our diagram, the angle will change a little bit. The algebra that we've already done is going to stay the same. So let's pick a convenient line to jump into. What has really changed compared to before? It's the acceleration. The acceleration is now 0 because we're going at a constant velocity. So let's pick up one of our lines and set the acceleration equal to 0. So we'll have f cosine theta minus mu k times n is equal to max. But ax is equal to 0. So f cosine theta is equal to mu k n. The solution for the normal force is the same as before too. So it's mu k times weight plus f sine theta. We still have f cosine theta on the left, mu k mg plus mu k f sine theta. We're just distributing the mu k. We're trying to solve for f this time. So we're going to subtract the mu k f sine theta to the left so that we have an f cosine theta and a minus mu k f sine theta is equal to mu k mg. And now we're in a place where we can factor out the f. So we have an f cosine theta minus mu k sine theta equals mu k mg. So now we're left to just divide in order to solve for f. So we have mu k mg all over cosine theta minus mu k sine theta. We know everything on the right, and we can solve for the force that would give us a constant velocity. So 0.350 times 15.0 kilograms times 9.8 meters per second squared over cosine of 25 degrees minus 0.350 times sine of 25 degrees. And all of that is equal to, let's plug it into the handy calculator. We get 67.8 newtons, which of course is considerably less than the 125 newtons that Gemma was pushing with before. And that should match our instinct about what the solution should be. Okay. All right, see you next time.